Hello guys, Happy New Year. I hope all of you are okay in the new year and ready for your exams. I will start today's lecture right after I get a confirmation that you can hear and hear me and I'll also spend some time at the end of the lecture to discuss about let's say some administrative issues regarding the projects. Okay, great. So I got a confirmation, so I'll start. So today I wanted to discuss with you about adversarial examples. And yeah, some interesting topics related to adversarial examples. And these are also how we can obtain models that at least not complete but some robustness to adversarial examples. So we will see different ways to fool CNNs with adversarial examples, and then we will also see how we can use these to copy models without having any information about these models. And just as a hint, so we used this approach in one of the Kaggle competitions to generate data for actually for the vision challenge. So if you're interested in seeing how the data was generated, just bear with me until the end of the presentation. So the presentation is based on some papers from the literature. So this is in 2014. It was discovered that neural networks have this problem with adversarial examples. So this is the first paper that we're going to discuss. And then some additional paper on the same topic that shows images that are not natural, but they can be classified with high confidence by neural networks as real data. Then we will see how we can use the same ideas to generate deep dream images. And then we have some another paper that tries to clarify better why adversarial examples happen, and provides a more robust explanation than what was previously thought. And then we will also see a paper that tries to improve models to avoid adversarial examples. And finally we will discuss about this final paper. And now I saw a small typo that I'm going to fix. Okay, so these are the papers for today, and I'm going to start with the first one. So this is a iClair 2014 paper, and the title is Intriguing Properties of Neural Network. So in their paper they also found this problem with adversarial examples. So but they also find other properties that seem to be intriguing. So first it was thought, so we have this let's say the first point. So maybe I'm going to go into details later and not explain them here, so we can better understand them with through the other slides. So first, their main findings are that there is no distinctive no distinction between high-level units and random linear combinations of these units. You will see what this means just in the next slides. Then they can also they also show that network can misclassify an image that has imperceptible perturbations, imperceptible to the human eye. So these are the adversarial examples, and they show that these adversarial examples actually can generalize well across different hyperparameter and datasets, and they generalize even across models. So they seem to be some sort of generic adversarial examples, so they fool all type of networks. So they explored these properties for 3 types of neural networks. So first they use various fully connected networks like multi-layer perceptron on the MNIST database. And then they also use 2 convolutional neural networks, one called AlexNet, which is the CNN from Krzyzewski paper, and also a model called CockNet, which is an unsupervised trained network. So regarding the first results that they observed, this is related to the interpretation of the higher level units. So in the first image, you will see that if you try to go on the pre-last layer units and try to see on what they activate mostly on, you will find units that activate, for example, to the lower round stroke. So this means this lower part here that is round. So these experiments are on MNIST. We will also see results on the ImageNet. So if you look at this, indeed there is a unit that seems to activate to this round stroke, and there is another unit that is sensitive to the upper round stroke, so sensitive to the stroke in 2 and 3s. Then is a unit sensitive to the left upper round stroke, so it's in left. So it's this part here, right? So it's could be a 5 or a 9 or a 6. So it's a round stroke in the upper left, and another unit that is sensitive to a diagonal straight stroke, and so on. So you will find that these different units are sensitive to these specific features, which is kind of interesting. But what is more interesting is that they found, okay, let's take these units, do a random combination of them, right? So you just make a random transformation of the units, a random linear transformation, and then you will find that these linear combinations are also sensitive to some specific patterns. So for example, in this case there is a random combination. So this is basically, if you look at these units as a basis in the space, so mainly if you change the basis, the axis will also represent the distinctive pattern. So here you will see once again a random basis that is that activates on the lower round stroke, on the lower left loop, so it's this loop for 2s, top round stroke, upper round stroke, and so on. So yeah, this is upper right round stroke. Okay, so you will find that these can also happen if you project these units in a new basis. So it means that actually yeah, you can find these units doing this projection. So it's a bit intriguing. It's not expected. So intuitively you would think that the network learns some specific features in the units, but as soon as you do this random transformation, then you will find that there are some random bases that also activate on specific patterns. It means that the phenomenon is a bit more generic. And the same happens, so those are results on MNIST. The same happens on ImageNet. So these are units that are sensitive to specific patterns like white flowers, round spikes, and so on. So this is green and yellow objects. So you observe this pattern, but if you do this random projection, you also see that you will find units that activate again to some specific pattern. So this is round flowers, dogs with brown heads, and so on. So yeah, this is the first property that they found. Then they also look at these adversarial examples and show that they can generate adversarial examples so that they can change the class of the objects. So in this picture, and we will see more examples such as these during the lecture. So essentially an adversarial example is an example that has a slight change from a natural example. So the change is so small that it's imperceptible to the human eye. For example, this image is modified from the original one, and here you will see the map of differences that is magnified. But if you look at these two images, you will not find any difference, and the same happens for these two images. And the problem is that the network, with this modification, it will no longer classify this example as a car. So the idea of generating examples works something like this. So first, usually when you train the network, you do gradient descent to minimize the error of the network, right? So you have some loss. So in adversarial examples, you try to do the same, only that the label that you're trying to predict is not the correct one, and you're not backpropagating the gradients. So actually, yeah, you're backpropagating the gradients through the network, but you're not updating the weights, you're just updating the input. So yeah, if you remember in the first lectures, we had this graph that we showed how we apply the chain rule on top of it. And if you think when you multiply x with the weights w, so you do the forward pass and you do the multiplication in a unit. When you do the backward pass, you compute the gradients with respect to x and with respect to w, but you update the weights w, and then for x, if it has a previous layer, you pass on the weights and you apply the chain rule again, and so on. If not, if x is the actual input image, then you don't need to compute the gradients because you do not update the image. But here, in order to generate the adversarial example, so that the most straightforward way to do it is to apply gradient descent on the input image instead of the weights. So you just keep the model frozen, and you try to do backpropagation in order to update the input such that the label becomes different than the actual ground truth label. And in the same time, so this is one part of the loss of the minimization objective. You also have the other part is to make sure that the difference from the original input is not that high. So we have this difference here denoted by R, which is like a random noise or something like that is actually optimized during the process. So you will obtain the example, the original 1x plus this modification R. And when you're optimizing it, you also want to make sure that your optimization minimizes this difference with respect to x. So what you want to obtain is to make sure that the network or the classifier, there are also experiments showing that adversarial examples can also exist for linear models. So they are not only characteristic to neural networks. So the main idea here, so this is the model F, right? The classifier could be a neural network or something else. We wanted to obtain a target label L, which is different from the ground truth label, and we also want to make sure that the difference is not very high and is within some bounded margin. Okay, so the objective would look something like this. So here you have the constant C that balances the importance of this difference of the original example and the the loss that is with respect to the target label. So yeah, this is the way, at least the first way that was proposed to obtain adversarial examples. And these are images that are obtained using this optimization process. So once again, you have this input image, you have the model, you forward pass the image through the model, and then you backpropagate and update the image according to minimize this loss function. And here you see the difference maps and the resulted images. So visually you will see that these images are the same. And here the target label was set to ostrich. So all these images are classified as ostrich. So here we have a bus, a bird, some sort of tower or monument, a dog, an insect, soap dispenser, and so on. So all these images are labeled as an ostrich. So this shows that naturally looking images, so these images with the naked eyes, we humans, we will definitely classify them as bus, dog, and so on. But the models, the machine learning models, cannot classify them accordingly. Okay, so here we have some results. These are results on the MNIST database with various fully connected models. So this is a fully connected models, a linear model with only 10 units. This is a model with 3 layers with 100 units on the first 2 hidden layers and 10 units at the end. And this is all an autoencoder. So these are some parameters for these models, and here you have the error on the training data and the error on the test data. And these are the errors of the models on the clean data. Okay, so here you have the average distortion that is necessary. So these distortions are quite small. So this is the average distortion that is necessary in order to have an error of 100%, or respectively an accuracy of 0% on the training set. So it means that with this distortion you can modify the image, all the images in the training, such that they are labeled wrongly. Okay, so this is not even applied on the test set, it works even for the training set. So yeah, it is quite bad. And here they also show in this table that these errors also generalize to some amount to other models. So for example, if you take the adversarial examples, right now I don't know exactly. Yeah, I think so. Maybe the adversarial examples are for the rows, and here you see the errors on the other models. Okay, so what this means is you generate adversarial. So when you do the optimization of the adversarial examples, you do the optimization for this model, and then you use the adversarial examples as input to another model, to this model or this model, and so on. So this is the error rate that you get when you test the adversarial examples across different models. So when you test on the same model, you always get 100% error. So this means, this means that the models are always the adversarial examples always work on the same model, but they can also transfer to other models at some degree. So for example, here if we take the adversarial examples from this model and use them on, let's say, this model, so this model has the test error of 20%, so here you can increase the error by around 3%. In some cases, so the adversarial examples for these shallow models are less, let's say, less robust, but if you look at adversarial examples for deeper models, so for example, if you generate adversarial examples for this model, for FC, for this fully connected network with 3 layers, you get you can increase the error rate of this model from 7% to about 38%. So it means that the adversarial examples are also adversarial for other models. And in the last rows here, they showed what is the performance if you just add. So here, you have the average distortion of the adversarial examples, and here they added some random Gaussian noise on the original images, and they tested to see how these models behave on these examples with random Gaussian noise. So it seems that this was just to prove that if you just add some noise to the image, the same problem will not occur. So it's in order to obtain the adversarial example, you really need to optimize it using this objective here. So if you just add some random noise to the example X, so if R here would be a random Gaussian noise, you will not obtain the same results. So of course the errors will increase slightly, but not as much as they increase with the adversarial examples. Okay, so this was to show that there is cross generalization over hyperparameters and over models, and they also have some results to show that there is also generalization over datasets. So what they did here was an experiment on the MNIST database, and they divided the database into the training part into two equally sized subsets of each having 30,000 examples. So and they used 3 models here. 2 of them were trained on this first part, and the third model is trained on the second part. So if you look at the training errors, the models are able to overfit the training, their training part, right? And they obtain an error of around 2% on the other part. So this is the baseline, the baseline results, the baseline errors, and this is the result on the test set. And these are the average distortions necessary to increase the error on the training set to 100%, just as before. And now they look at how these examples that are generated, for example, so these are examples generated for this model on the first part. So if you look, it will also apply to this second model on the first part, but it also increases the error rate of this model trained on P2. So the same happens for this other model. So of course the examples are generated for this model that's trained on part 1. So it brings it increases the error rate for both other 2 models. And the same happens here. So this is the same architecture, and this one only trained on P2, So you get 100% error here, but these two have also higher error rates. So yeah, if you can compare these numbers with these numbers and see that they are higher in general. Okay, and here they also have a distortion with a higher standard deviation, and these can actually provide even worse results, and even across the databases. Okay, so yeah, if you're allowed to go to a higher standard deviation, you will see that the error rate grows higher. Okay, so these standard deviations are quite small, given that the examples are represented in the zero, so the interval for the pixels is 0 and 225. So it means that here you just modify maybe a few pixels in order to transform the example into an adversarial example. Okay, and they also make this this analysis regarding the instability of the model, and what they do is they look at these Lipschitz constants for every layer. So here we have the model phi, which can be seen as a composition of the functions phi k, where k is the number of layers of the network. So here we have the first layer applied on the input and the parameters with the parameters w1. Then we have phi2 applied on this input and the weights w2, and so on. So this is the neural network, and each phi k with small k represents a layer in the network. So if you look at the average difference between the activation of each layer with respect, so given the examples X and the modified examples, the average, the norm of the difference should be smaller than this Lipschitz constant, which is multiplied with the magnitude of the change. Okay, so essentially this tells us how much this layer varies with respect to the variation of the input X. Okay, so they compute these constants, these Lipschitz constants, for these layers of the AlexNet architecture, and they expect that adversarial. So the conclusion is here. So if you have large bounds, then these do not necessarily mean that there exist adversarial examples. But if you have small bounds, you might have a guarantee that such examples will not appear. So one way perhaps to obtain a model that is robust to adversarial examples is to make sure that these Lipschitz constants are very small, and perhaps you can add this constraint to the optimization, but it might be a very painful process because you have to add this constraint through every possible layer, and this is a constant that is computed on whole data set. So here we have for all X, so it is quite expensive to optimize, I think, but at least it gives you some theoretical idea of how to obtain models that are robust to noise. Okay, so yeah, we will move slightly towards looking at why these adversarial examples exist. So yeah, it means I think it mainly boils down to the fact that these models are essentially linear. So mainly, yeah, linear, if you think about a single layer. So yeah, in the end, in the final representation that you get just before the classification layer, you have embedded the data into a space, and then you apply some linear classifier on top of that. And I think the main problem is also linked with the curse of dimensionality. So essentially, you have these examples, these training examples that are embedded in this dimensional space, and these are actually embedded only with respect to some direction. So for example, the objects that are typically seen in the training data are dispersed on this axis, and if you look on the other axis, you have no data to fill in the space, and you can easily construct adversarial examples by going into this area of the space. Okay, so mainly, yeah, in this area the boundary is loose, and the model is not confident in the predictions. Okay, so there is one intuition in this paper that generative models, because of this property, would not be so easily fooled. But there are some more recent results than this paper that are actually also included in the presentation that show that also generative models suffer from the same problem. Maybe not as the problem is not as bad, but it's still yeah, quite bad. Okay, so yeah, so these results were so some of these ideas were proposed in the Eichler paper of Goodfellow. So they concluded that adversarial examples can be explained as a property of these high-dimensional dot products, and we will discuss more on this. I think, yeah, we have the paper, maybe the third or fourth paper. We will refer to this again, and they show that, yeah, as I explained before, because the models are too linear, and this is why also examples can generalize across different models, and because adversarial perturbations are highly aligned with the weight vectors of these models. Okay, so the next paper is on deep neural networks are easily fooled, high confidence predictions for unrecognizable images. So this is somewhat related to adversarial examples, but here they show larger variations of examples that are adversarial. They go in another direction, so the examples are not necessarily natural images, but there are images that are not natural, so it's clear for the human that these images cannot be classified as any of the object classes, but actually the model classifies them with very high confidence as one of the classes. So yeah, we kind of also exploited this property in the dataset used for the computer vision challenge on Kaggle. So in the same way, you can generate images yeah, to be classified in certain classes. Okay, so the question that we're looking at is, yeah, given that these models, so I think we mentioned in the previous slides that convolutional neural networks achieve very high performance on ImageNet and even surpass the human level performance, and they start from this question: then what are the differences that remain between human and computer vision? And actually it seems that there are quite big differences with these adversarial examples. So I hope, yeah, I have this YouTube video prepared that is a really good presentation of this approach. So I'm going to try to re-stream it for you.
The human brain recognizes objects by extracting multiple layers of representations from a sensory input. Inspired by the brain, deep neural networks have demonstrated excellent performance in many classification tasks such as voice recognition and natural language processing. They are especially good at vision recognition. The networks can nearly match a human's ability to recognize objects in real images. That raises the question of what differences remain between how deep neural networks and humans see the world. The answer is quite a lot. A recent study revealed that changing an image originally correctly classified, for instance as a school bus, in a way imperceptible to humans can cause a deep neural network to label the image as something else entirely. In this research, we show a related phenomenon that deep neural networks label images that are unrecognizable to humans as school buses as well. While some deep neural networks can recognize guitars with high confidence, we can find certain unrecognizable images that these networks will also rate with 99% certainty as guitars. Our research shows that it is easy to produce such synthetic images that are completely unrecognizable to humans, but that deep neural networks believe with near certainty are familiar objects. For example, a state-of-the-art deep neural network believes with 99% certainty that these images are bubbles and peacocks, but they clearly don't look like real bubbles and peacocks. We generate these synthetic images with evolutionary algorithms that produce images that deep neural networks confidently label as belonging to a class. To do so, we take a deep neural network already trained to recognize real images. Then, we evolve images that the same network rates confidently as known objects. We evolve two types of images. The first type is directly encoded images, meaning we independently optimize the color values of each pixel. The resulting images look mostly like white noise. The second type of images is evolved with an indirect encoding, which produces images with more regular patterns. Previously, evolution with this encoding has produced images that are recognizable to both humans and deep neural networks. While the type of images is different, the result is the same. Images are produced that are completely unrecognizable, yet the networks classify them as familiar objects with certainty. We repeat the experiment on a different network that performs well at recognizing handwritten digits. Evolution is asked to generate images which are confidently labeled by the network as digits. And we observe a similar phenomenon. This is what the images are supposed to look like, but the network believes that these images are real digits with near certainty. One may ask how deep neural networks can label these unrecognizable images in a way totally different from how a human would. Looking closely at the images, for example the jackfruit, we think that the network may be looking at these yellow pixels which somewhat vaguely look like the real jackfruit. Some images appear with the right colors of the class. The starfish has a blue of water and the orange of skin. The remote control image has a grid of buttons but no rectangular contour of the device. Instead of looking at the global structures of an object to make decisions, deep neural networks tend to look for discriminative features such as colors or buttons to determine if this is a jackfruit or a remote control. This is a curious result that allows us to better understand how deep neural networks work, such as what they learn to focus on when classifying images. But why does it matter? One can imagine a security camera relying on deep neural networks being compromised when white noise images are swapped for face or fingerprints. A shady company could inject explicit photos in Google search results to make profits. They could bypass Google image filters powered by deep neural networks by producing explicit photos but that the networks recognize as safe content. Interestingly, letting deep neural networks drive the evolution of images also creates an automated art engine that endlessly generates diverse abstract art. In this paper, we have shown a major difference between how human vision and state-of-the-art computer vision recognize objects.
Okay, so this was the presentation. I hope it all went well. So you also have the link in the slides, and if you want to watch it again, you will have the possibility to do so. Okay, so yeah, this is the paper that we want to present. I just used this presentation because it was very nice, and you can get the gist of the paper from the presentation. So what they did in their experimental setup, they used a LeNet model on MNIST, and they also used, as in the previous paper, an AlexNet model trained on ImageNet. So they have results on the MNIST and ImageNet with these two neural networks. And as shown in the slides, the framework is based on a state-of-the-art DNN that is trained with high confidence. So we have here LeNet or AlexNet, and if you give it some input images, you will get the output from this neural network, and they apply the same loop here, only that in between these two steps. So they get an input image, they pass it to the network, they get a score, and then they use the score in the evolutionary algorithm to improve and to select or to mutate images, to do crossover, and select images that obtain higher confidence scores. So during this process, so you get a new, let's say you start with a population of images, you pass it through the network, you obtain some scores, you take the better individuals, those that have higher confidences for certain classes, you select them, apply crossover, do mutation, add these new examples to the population, and redo this process until you optimize the images as you desire. Okay, so they used grayscale images for MNIST and hue saturation values for ImageNet, and the pixels are initialized with random uniform noise in the range 0 and 2025. So they used this range, and the numbers are independently mutated. So this is the first type of adversarial examples that they obtain, and these look mainly like some sort of random noise. And yeah, if you look, there are perhaps some so these are labeled with this class. So this is a robin, and there seems to be some pattern here that looks like a robin, and the pattern here that looks like an armadillo, and this maybe looks like the head of a cheetah, and so on. But mainly they look like random noise, and these examples are actually classified into these classes, which is shouldn't be right. Okay, so this is the algorithm based on direct encoding. So it's a basic generative, not generative, genetic evolutionary algorithm, and they also use this alternative approach that is based on a compositional pattern producing network. So this approach is, so they use a network that produces these compositional patterns, So these are generated like some sort of let's say a primitive generative network. In our Kaggle competition here, we actually and in the black box Reaper paper, we actually used a generative adversarial network that was capable of generating more realistic images, let's say. So yeah, this so they use this network to generate images, and then they apply the evolutionary strategy for these images. Okay, so yeah, the algorithm is basically the same, only that here when they generate the images, they apply this network, and then when they generate the new population, they actually change the parameters that they use as input to the CPPN in order to generate a new population. Okay, so okay, there is also this approach that like kind of a baseline for them, showing that if you apply gradient ascent on these random noise images, you get similar results, but actually these are more salient than their results. And they actually claim that using generative genetic evolutionary algorithm is better. Okay, so these are examples that are labeled as, so here you see the labels on top, and you have several examples with the same label. So this is class 0, this is class 1. So here for class 1 we see some vertical patterns, but I think for the other classes it's really hard to distinguish any patterns in these. Okay, let me see. Okay, so I had a problem with the software. Okay, this is probably caused by an update of the OS. So let me know if you can still hear and see my slides. So if everything is okay, I will continue with the lecture, but it seems that there is also a problem with PowerPoint. So let's go back to this slide. Doesn't want to work. Okay, so first just please write something down in the chat if you can still hear me well. Okay, so yeah, let me try to reopen PowerPoint and see if that works. So the slide was here. Okay, so it works this time. Okay, and these are examples generated with the CPPN, and once again these are some random patterns here that are classified with 99% confidence into these classes. So once again we observe, for one, we observe these vertical patterns here, but for the other classes is not really clear. So yeah, maybe this is maybe the only intuitive pattern that we can find. And the same happens for ImageNet. Here they try 20,000 generations to evolve the images, yeah, there are some images that have high confidence, but not all of them. And here they say that they were able to produce images with confidence higher than 99% only for 45 categories. So and yeah, the median confidence is around 21%. So it seems that ImageNet is, or AlexNet is more robust to this variation. However, for CPPN, the results were more successful. So after 5,000 generations, the median confidence is almost 90%. And yeah, they were obtained many images with confidence higher than 99.99% that are unrecognizable. So there seems to be a certain category of classes from index about 100 and something to 300 that are they were not able to obtain these type of adversarial images. And here they show results. These are taken from the paper. So yeah, maybe this was an idea to guess them, but you already saw the presentation. So yeah, this is a penguin, this is a starfish, and they also explained because this pattern looks like a star and this looks like water, and this has the patterns from the baseball, but it's not an actual ball. So this is more yeah, if you look as a general observation, is that these images are classified into these classes because of their texture mostly. Okay, so they also analyze that and see that these images are also related to each other. When they generated these images, they observed that, for example, for this small dog, spaniel or Pekingese, they obtain generally obtain these patterns that are very similar to each other, and the same happens to this to lizards and other reptiles. So the images have generally patterns that look something like this. Okay, this is a different one, and they obtain the same type of similar images, but with different patterns. So it's not always that all the images look like this, but for these classes, the images that are generated can look quite similar. But there is also some variation within the class. Okay, they also did an ablation study with respect to the repetitive patterns. So perhaps there was some claim from the reviewers that these patterns, so the networks are full because these patterns are repetitive. So if you try to eliminate some of the patterns, so for example in this image, if you just keep this pattern here, you will still be able to classify it as lipstick, even if you eliminate most of the repetitive part. The same happens here to the class ruler, where you eliminate some of the repetitive patterns, and for oboe. Okay, so okay, and then they also try to address the problem if DNNs learn the same discriminative features or not. So they have two DNNs, DNN A and DNN B, and they try to do cross model evaluation. So if you look at the top matches, you will find that many images are in the same top one prediction. So yeah, this is these are the top one matches. So here we have DNN A applied on DNN B images, and DNN B applied on DNN A images. And when you do the cross database results, you obtain about more than 60% of the top one matches are the same. Okay, so Yeah, so this is another interesting result. um, they also tried to add a fooling images class to the models, so to see if they can improve the let's say the so the main idea was to try to make these models to make them robust to such generated examples. So if you recall the examples that were generated for MNIST with CPPN, they were slightly different than these. And when they added those images into the training data as a new class and trained the whole network with this extra class, they were still able to generate other images with very high confidence into the 10 MNIST classes. So these look different, but they all have very high confidences of being in the respective class. So even if you try to add the adversarial examples into the training, you can still find new examples that are adversarial. Okay, so they observed that for ImageNet, the median confidence score decreased from 88% to 11%. So for ImageNet, it seems that adding these adversarial examples to the dataset into this special class and labeling them accordingly really works better than MNIST. So it's not as easy as before to generate this type of images. Okay, so this was the last thing about this paper. Next we discuss about Deep Dream. So here Deep Dream, maybe it's not related necessarily to adversarial example, just to the process, the optimization process that is used to generate these type of artistic images with neural networks. So what you do is you apply the same idea, you backpropagate the gradient, but instead of updating the model, you update the image, the input image. And in addition to the loss function, you want to let's say magnify or to increase the activations for some specific units in some specific layer that you choose. So in this way, when you want to so remember that those units in the first paper that we showed, they activate on some specific patterns. So first you look at these units and you see on what patterns they activate, and then you can try, okay, I want this unit to activate more for this image. And then when you do the backpropagation and you modify the input image, you generate these images that look like dreams. So this was the human observation. They look like dreams, and they named the approach Deep Dream. So here, for example, I think for this image they try to emphasize the units that, or you can actually emphasize the activations for an entire layer. And if this layer is an layer high in the hierarchy or near the output, it means it will increase or try to modify the input image, and it will generate high level patterns like birds, dogs, and object parts. If you apply this at a lower level, so for example, if you maximize the output of an input of a layer that is closer to the input, then you generally perhaps obtain images with these low-level patterns. Okay, so yeah, these images are obtained with the same technique, but they are optimized with respect to a different layer of the neural network. And these are some images that are generated with deep dreams, and they look like some sort of inception landscapes. So in their setup, they applied this deep dream algorithm on the Google Net architecture. So they just use the technique is pretty simple. They use gradient ascent to maximize the L2 norm of the activations of a particular layer, and there are only some tricks perhaps involved in the training process. So they use an offset to the image that using a random jitter. They normalize the magnitude of the gradients in the gradient ascent step, so that they make sure that the gradients do not explode. And yeah, they apply gradient ascent across multiple scales of the image. Okay, so they can also control the dream, as I said, with respect to some layer. They can also modify the objective to make sure that the generated image has more diversity, so it doesn't have a preference to, let's say, add patterns of chickens. Just make sure that it tries to add more diverse patterns. So this can be achieved by maximizing the dot products between activations of the current image and their matching correspondences from a guide image. So you can add another guide image to the process in order to control the dream. So here you have this input image, and you have this image. So you do the dot product in this layer that you want to emphasize between these two images, and then you optimize this image such that it increases the dot product. So it will generate patterns that resemble this image into this image in order to maximize that dot product. Okay, so this way you can diversify your dreams and obtain different image patterns. And you also have this website that I think is still working. So you can add an image and generate a deep dream with it, and you also have the code to do this. Okay, so moving on to the next paper. So I mentioned at some point that the main explanation for the existence of adversarial examples is due to the linearity of the models, and this was shown experimentally in this paper by a large part of these of the authors from the first paper are also authors of this second paper, which is entitled Explaining and Harnessing Adversarial Examples. Okay, so I don't know, I have a sensation that here the text is not the same size. Well, it is. Okay, so okay, so yeah, the highlights of the paper. So they mention in this paper that the previous explanations for the existence of adversarial examples are more speculative. They show actually here that the flaws are in the linear nature of these models. They also introduced a new method called fast gradient signed, which seems to produce adversarial examples more quickly. They also discuss about adversarial training of deep neural networks. Also try to explain why adversarial examples generalize. Okay, so in their first work, we have seen this vulnerability of machine learning models to adversarial examples, and they proposed two explanations. So first, the models are because they are extremely nonlinear, so this loss function is very complicated, is a very complicated surface, and then it is very easy to find adversarial examples in this space. So it seems that this is not the case, and the other speculative explanation is the insufficient model averaging or insufficient regularization. It was proposed, as I mentioned earlier, with the analysis of the Lipschitz constants. If you add regularization with respect to these Lipschitz constants, you will be able to reduce or eliminate adversarial examples. And they also show that this is not the case. So the actual problem is that models behave linearly. So what do they mean by this linear explanation? So if you look at some adversarial examples, so here the noise that is added is denoted by nu, and this noise has some upper bound epsilon. So the upper bound is imposed in order to make sure that the examples or the change is imperceptible to the human eye. And then when you consider the dot product, so if you take let's say a layer in the neural network, you have the weights that are multiplied with this adversarial example. So if you consider that the adversarial example is equal to the original example plus this noise pattern, it results that what you do here is you multiply the weights with x and you add up the weights multiplied with the noise. So it means that the activation, so the result of this dot product is the activation of the layer. So if you change this noise pattern, it means that the activation will grow linearly with respect to the noise pattern that you introduce. So in order to maximize your growth, you can use this noise pattern as the sign of the weights in order to maximize your growth. So just to make sure that you go in the same direction as the weights, but as far as possible from the input. And this also gives the idea of the fast gradient signed method to optimize adversarial example. So of course this is done by still dividing the noise, so the norm has to be lower than this epsilon. So we divide the sign with the norm. Okay, so the idea is to add these linear perturbations. So of course this works in the same way. You update the input and you keep the model fixed. So for some input x, the update, the noise is going to be equal to the sign of the gradient of the objective, which is determined by the parameters of the model, the input x, and the desired label. Okay, so so this is the updated is added to the image, and then you obtain an adversarial example, which is given by x times the norm applied to this noise in order to make sure that the change is imperceptible to the human eye. And then you get a different class. In this case, the class is Gibbon with 99% confidence. Okay, and they also show these experiments with the fast gradient sign method applied on logistic regression. So logistic regression applied directly on the pixels of the MNIST database. So this is a linear model, and if you just use the weights of the model, so in the classic approach, you can obtain an error rate of 1.6%. So it would seem that the linear model would be robust to adversarial examples, and perhaps this is why they initially concluded that this applies more to deep models. Adversarial examples exist more for deep models, but if you use the fast gradient sign method, so if you use the sign of the weights, then you obtain these adversarial examples that have a higher error rate for the logistic regression model. Okay, so yeah, it's clear. So these are visually different from the input, but you can still find these examples with very high confidence of being wrong. Okay, and what they proposed is to use this approach to train deep neural networks. So to the standard objective, they used this additional objective. So they also try to minimize the objective with respect to the gradient sign. Okay, so using this approach, they were able to reduce the error rate from 0.94 to 0.84. So this gives an improvement to the model when it is applied on original or on clean training data, but it still has this is a different slide. It still has some problems with the adversarially generated examples. Okay, so it is an improvement, but it doesn't solve the problem with adversarial examples completely. Okay, so what they this is regarding the initial comments in the paper. So they initially thought that models with low capacity were enabled to make different confident predictions, and actually if you use RBF networks, this is not the case. So RBF networks are really confident about their predictions. The problem is they generally obtain lower results. So how they tested this hypothesis is to use a shallow RBF network without any hidden layer on MNIST, and the original error rate is around 55.4%. So it's not a random a classifier with random decision, but it's far lower than LeNet, let's say, or other models with higher capacity. So the error rate on clean training data is quite high, but if you try to generate adversarial examples, it has a low confidence. So for example, for the mistaken examples, the confidence is only 1%. So it's quite sure that the examples that are not quite sure, but yeah, the for the mistaken examples the confidence is quite low. Okay, and the problem with the error rate, of course, is that the model is not invariant to significant transformation, so it means that the model does not generalize pretty well. So it is a model that is robust to adversarial examples, but its capacity is not as good. Okay, and they also analyzed in the paper, so they have a section on explaining why adversarial examples generalize so well. So they look at the adversarial examples in the pre-last layer, so in the subspace generated from the pre-last layer of the network, and they look at certain direction that has positive dot product with the gradient of the cost function, and here epsilon is the noise, the magnitude of the noise of the adversarial examples. So yeah, they essentially in this plot, so they show that the behavior for each of the 10 classes in MNIST is linear. So yeah, these models are actually for each class you have a model that is composed of some linear components, and yeah, they're mostly linear examples. So these are some, if you look at the patterns here, they look like ReLUs with I don't know, various slopes that are combined together. So the models are generally linear with respect to the magnitude of the noise. And for one of the classes, for class 4, they show how so this is the magnitude of the noise. So this is the example, and as you increase the magnitude of the noise, so if you go further away, you see that the behavior is quite linear in the adversarial example. So it goes in about the same direction, that it's kind of orthogonal to the model. Okay, so they conclude that a significant proportion of the errors are consistent with the linear behavior of the model, and this is the major cause of the cross-model generalization, and also explains why the adversarial examples exist. Okay, and they also try alternative hypotheses that were proposed in previous works. So first, there was one hypothesis that generative models are robust to adversarial examples, and another hypothesis was, okay, if we build an ensemble of models, we can also increase the robustness to adversarial examples. So they test on the MNIST database, they test deep Boltzmann machine, and with an epsilon of 0.25, and they obtain an error rate of more than 90% on the adversarial examples. So it means that the generative models are not robust to adversarial examples. And they also try an ensemble with 12 networks with max out activations on MNIST, and again the noise magnitude is set to 0.25, and here they obtain 91 error rate on adversarial examples on MNIST, whereas one member of the ensemble can have the error of 87%. So this is one of the members can, in this case, one of the members had a lower error than the ensemble. So using ensemble is not really good idea. So it has some resistance, but it's very, very limited. So yeah, these are the conclusions. So in the end, in this paper they discovered that adversarial examples are a result of models being too linear. The generalization of adversarial examples across different models occurs as a result of adversarial perturbations being highly aligned with the weight vectors, and you can exploit this to generate adversarial examples using the fast gradient sign method. And yeah, adversarial training can result in regularization, but it doesn't really solve the problem of adversarial examples. Okay, and yeah, they have, this is an extended set of conclusions. So they also shown that generative models or ensembles are not resistant to adversarial examples, and linear models lack the capacity to resist adversarial perturbation. So it seems that it is better to use deeper models, because at least for these models you can try some approaches to avoid adversarial examples or to improve the robustness. Okay, so this is another paper that deals with improving the robustness of neural networks to adversarial examples, and the main highlights in the paper. So they also tried to. One idea was to use pre-training to improve the robustness, or see how this actually behaves, and they discovered that using denoising autoencoders as a pre-processing step is actually worse than just training the model end-to-end. So using pre-training seems to make the network even weaker to adversarial examples. And they conclude that the network sensitivity to adversarial examples is more related to the intrinsic deficiencies of the training procedure and the objective function than the model topology. So it's more related to these aspects. Well, this is in kind of a contradiction to the other paper, so they reached to a different conclusion. Anyway, so the conclusion, it's actually maybe just a premise for their approach, for the approach they propose, and they show that this approach also, it's more actually more looks more like a regularization approach, and does not actually give robustness to adversarial example, or the robustness is not as high as expected. Okay, so what they propose is to use deep contractive networks as a robust model for adversarial examples. Okay, so first they study the injection of noise. So this is a simple Gaussian noise, and see how the test error on clean data increases. So as you add noise, you expect the error on the clean data to increase. And also on the left side here we have adversarial examples, and so this already includes some noise patterns that make them adversarial, and on top of them they try to add this standard noise and see if if the test error goes back into the original model. So interestingly, if you add these noise patterns into the adversarial examples, the test error starts to decrease, and you reach a point where the noise is around the deviation is around 0.5, where you can get higher error rates for the original examples than from the modified well, not higher, sorry, so these are different axes, but they get closer. Yeah, so they also look this from for different architectures. So actually, yeah, we also have here autoencoders, convolutional networks, and networks with two-layer perceptrons. Okay, so yeah, if you look at the test error on clean data, this is the test error on clean data, and on the right you have the test error on adversarial data. And if you blur the images with a kernel, you can so for the clean images, you slightly increase the error rate, and for these adversarial examples, the error rate decreases significantly. Okay, so here the idea was, okay, so if we have these images and if we add noise, we can improve the results. Maybe if we also add Gaussian blurring, it might also improve the results. So here they see that you can go to a kernel to size up to size 5, and you get some good results. But if you go to a higher a kernel with a higher support, then the error rate goes back up here. So yeah, this is a kind of a limited approach to remove the adversarial examples. Okay, so but yeah, it reduces some of the adversarial examples, so it seems to be a good idea. I'm not sure if they thought or anyone tried to use perhaps a median kernel here. Maybe that would have been even better. Okay, so these methods are only partially effective in removing the noise, and the error of the adversarial example goes down, but it doesn't match the error on clean data. So these methods alone cannot solve the problem with adversarial examples. Okay, so what they propose to use deep contractive networks. So they inspired themselves from contractive autoencoders. So actually these slides, I already presented them when we discussed about autoencoders. So given that the time is passing by fast, I'm going to skip them. So just to recall that contractive autoencoders are autoencoders that have the embedding layer has more units than the input and the output, and in order to make sure that it doesn't learn a trivial mapping here, you add a regularization term, and the regularization term is based on the Frobenius norm applied on the Jacobian matrix, which contains the gradients of the encoder with respect to the inputs. Okay, so this is applied, so this is the idea for contractive autoencoders, And if you go to deep contractive networks, the idea is to add this regularization term to the neural networks. And for a network with h hidden layers, you are supposed to add this regularization term for each hidden layer of the deep contractive network. And this seems to be quite expensive, so this formula applies to every hidden layer I. And they also show in the paper a more so it's not included in the slides, but they have a way to approximate this objective on the whole network, so you don't need to do it for every layer. And yeah, this is the DCN with average with adversarial distortion. So you get the error here of on the original. No, I think this is the error on adversarial example. Yeah, this is the original error. This is the distortion of the examples, and this is the distortion of the original model. Actually, no, I think this table contains the yeah, now I recall. So this table contains the results of the original architecture and the deep contractive architecture. So when you add that regularization term on the clean data, you get some increased error rate, okay, but here if you look at the adversarial average adversarial distortion necessary to reach 100% error on the adversarial examples, you will see that generally you need higher distortions in order to generate these examples. So they quantify their success in terms of the average distortion necessary to reach 100% accuracy on the test set. So you are still able to generate adversarial examples, but now you need a higher distortion in order to obtain this. Okay, so let's move to the final paper. So as I mentioned earlier, this was used to generate images for the Kaggle competition. So this paper was presented last year at NeoRIPS 2020. So the idea here is to try to copy the functionality of a model. For example, on an API, a model that is exposed through an API, for which you can only have access to the output for some input images that you pass to the model. So you don't know anything about the architecture of the model, the hyperparameters, the weights, and so on. So all this is supposed to be concealed, even the training data set. So yeah, the only way to access it is to make this API call. Okay, so what we propose is a novel generative evolutionary algorithm that steals the functionality of these black box classification model. So it doesn't require any information about the training data, the architecture of the parameters. So it means that it is applicable to APIs. And it also outperforms methods that steal the functionality that are not complete black box models. Okay, so the objective actually that we want to optimize is yeah, we want to make sure that the output of the model copy, so S here. So yeah, we frame this in a teacher-student framework where the teacher model generates is the black box model for us, and the student model is the copy that we want to train. So here we use we have the training set X that is only accessible to the teacher model, so we are not able to obtain, or we do not know the X here. We have a bunch of test images X prime, so here in order to make sure that or to test that the student reaches the or is close to the accuracy of the teacher, we have this test set that is from the same distribution of the training model, so the teacher is supposed to obtain very good performance on this test set, and what we try to do is to train this student on a proxy data that tries to behave as good as possible on this test data X prime. Okay, so we assume that we have access to X prime only for the purpose of evaluating the student. So during training, we use a different training set, which is called the proxy data set. So here we have the arrows indicate the forward and the backward passes through the model. So this means that we do training on Z and we just test on X. Here we do training on X and we test on X prime. And our objective is to minimize the output of the student with respect to the output of the teacher. So the difference between the student and the teacher has to be minimized. Okay, and in order to minimize these objectives, we have this architecture, so which is based on 3 steps. So in the first step, we have this random noise vector that is passed through a generator. So the generator can be a variational autoencoder or a generative adversarial network or any other generative model. Then the generated example is given as input to the teacher, which produces some label. Okay, and then we apply genetic evolutionary algorithm to modify this population of noise vectors to maximize the output of the teacher for a certain class. So we try here to generate an image, so that activates for a certain class of the teacher. Okay, so even if the image is generated and the generated image is the generator is trained on the proxy dataset Z, so these can be completely different classes from what the teacher is trained on. So we generate this image, we pass it to the teacher, it gives us some output, and then we try to modify this generated image with evolutionary search that is applied on the latent space of the generator in order to obtain an image that is closer to the desired output. Okay, and then so this is in the second step. We do the evolutionary search. Okay, and in the third step, once we have optimized this example, we take it and we give it as input to the student, and we want the student to reproduce the same output as the teacher. And yeah, this is the algorithm that we propose. So yeah, given the time constraint, I'm not going to go through the slides here, just to visualize some results from the paper. So here we have a data set with cats and dogs that is used as proxy, and we have a target data set with a different species of monkeys. So here we have this image, an image of a cat that is optimized through evolutionary search towards an image with high confidence as a squirrel monkey. So this is an image from the original data set that is the most similar one to the generated image. Yeah, so this image is labeled with very high confidence to this class, and so essentially this is an adversarial example for this class, but we use this adversarial example to train the student, so to make sure that the student, when it sees this image, it will give us the label squirrel monkey. So the same happens to this other example. So you have a picture of a dog, and we try to optimize it through evolutionary search in order to give high confidence for the class bold Wakari. So it becomes an image like this. So this seems to resemble this monkey with a red face here. So it transforms the nose of the dog into this the kind of face of the monkey, and then again the student is trained on this optimized image. And yeah, we compare with some baselines from the literature. So these baselines are not so the only baseline that is also a black box, I think, is knockoff nets, and the other baselines have some partial access to the model. So in this case they do backpropagation through the teacher model, so it means that they have access to the architecture of the model to do backpropagation. So the main trick here, maybe I missed that point, is to use, in our case, was to use generative evolutionary algorithm, and thus avoiding the requirement to have access to the model weights. Okay, so this was the state-of-the-art paper in literature, and in 3 cases here we are able to obtain better results, and on top of that our model, our teacher model, is also a black box for us. Okay, so this is doing transfer from CFAR 100 to CFAR 10. This is doing transfer from fashionist to CFAR 10, and here we test 2 different architectures and various baselines, and we also show here the benefit of doing evolutionary optimization in this case. So if you do not use the evolutionary optimization and you just use the GAN, you obtain lower performance. And if you add in the evolutionary optimization, you can get results that are much closer to the accuracy of the teacher. So the target here would be to reproduce these results here. So you see in general that the results are lower, but in many cases they are quite close to the target. Okay, and these are results with 2 data sets as proxy. This is images of faces and images of cats and dogs, and here the target was the 10 monkey species data set. Okay, so in summary, yeah, we proposed a novel generative algorithm for stealing the functionality of the black box classification models, The model doesn't require information about the training data or the architecture or the parameters, and it outperforms the state-of-the-art approach. Okay, so this was the last slide. So now we have time for some comments. Okay, I forgot to look in the chat and look for questions. So there is a question, but I'm not sure now what is related to. Maybe, yeah, I know. Maybe the slide, this slide here. So the question is, let me just put this on another screen. So the question is the noise approach related to how much noise the machine learning model learns from data? Yeah, so essentially perhaps you mean how much the model overfits. So yeah, probably if a model has higher level of overfitting, maybe it will be less robust to noise. So here it seems that, yeah, deeper models generally have yeah, actually no. If I look at this model, so this is a plain model and an autoencoder. Yeah, so maybe, but this is a bit of it's not clear here. Yeah, there seems to be some influence of the loss that is used, like L1 or L star. Yeah, so at least for the convolutional networks, if you add noise, you are able to improve the error rate on the test by a significant margin, more than the other models. And whereas here, yeah, the conv network seems to be less robust, this one, but the other one is more robust. So I think, yeah, in general the L1s are more robust to noise, and this depends on the loss. I'm not sure that the L1s are doing less overfitting or not. It could be an explanation. Oh, okay. So you mean in a more general way that models are unimportant? Yeah, they from the paper with the generative evolutionary strategy of generating adversarial examples, we saw those CPPN images that look like that are patterns, right? So they look for different things than what humans look for. So they seem to look for textures instead of trying to comprehend the general object. And perhaps, yeah, but this is automatically, right, that the models are automatically learned from data. So perhaps from the datasets that we have, it is sufficient to learn to discriminate images using these patterns of textures. Okay, so yeah, I promised in the end, so it's quite late, so I'm going to try to discuss about the administrative part. We are going to so for the next week, but before the lecture, although I think we will not make a lecture. In the same day, maybe starting from 10 a.m. We will see the presentations of the projects. So I'm going to send some meeting links. So there will be presentations in parallel with me, Petru, and Antonio. So everybody will be distributed to one of us, and we will have 3 different links for the presentations, and I'm probably going to share. So now it's still have to edit some things here, but we'll probably share this document with you, so you will see when you are scheduled, and what is the link for the that you have to use for the presentation. Okay, I'm also showing this because I wanted to ask you. So there are some people that participated in both competitions, in Vision and in NLP. So for some of them, so for example, let's take this first example here of Alexandra. So I assume that here, well, actually this one is, yeah, it's here, right? Yeah. Okay, so I assume that Alexandra wants to present this project because here it has a higher starting rate than in this case. So yeah, we will I assume that she will present the NLP project, and this spot in the rank is eliminated, and now the next person after that gets a 9. So for all these grayed out people, they are eliminated from the ranking because they appear in the other ranking in higher positions. Then there are some people with blue that can also get these extra points. For these 2 guys, we have they are in the top 10 in both rankings, so they have to decide which one to present. And also for these, they are in rankings between 10 and 20 in both rankings, so this means that they get an extra point. But they still have to decide. So these guys that get an extra point, they have to present both projects. So this is mandatory for these 3 guys, and they also have to decide, maybe give me an email. So they have to decide between the main project. Okay, so the idea, yeah, they have to present both projects, but one of them will be the main one, and from the other we will eliminate them from the ranking. And the same applies to these 2 guys. They can also opt for Vision or NLP, so once again we can eliminate them from the ranking once we know their decision. Okay, so if you will communicate this information before the presentation, we can update the starting grades before. If not, at least during the presentation we will have this information and know the starting grades. So perhaps these grades will update depending on these choices. So maybe here or here, we don't know. And there are also these 2 guys that should let me know. So I mentioned that you need to use your full name in the competition, perhaps next year I'll make sure that people that do not use their full name will be excluded automatically. But now just try to email me to claim these two accounts. So whoever participated in the competition with these names, if it's no longer possible to change your name, just give me an email claiming your account, and also give a print screen that shows that you're logged in with this username, so to make sure that this is indeed a person that you're claiming. Okay, so so as I mentioned, next Thursday we will set up some schedule for the presentations. I think you need to upload, so I'm not sure if you already uploaded. So yeah, the deadline is on 7th, so today. So yeah, perhaps it could be useful to yeah, I was thinking maybe we have, so you can I will communicate. So if you haven't submitted your projects yet, okay, so for Andre, so since you have 10 in both, you don't need the extra point for the other project, so you can just choose the one that you want to present. Okay, so what I wanted to say, but I don't remember now the email address for the deep learning course. So we have a Gmail account for the deep learning lectures. So you will be asked to submit your project documentation and code to this email address. I know here, I think it's written that you have to submit it to your lab supervisor, but I think it's better to submit it to this joint email address. So I will communicate. I have to look for the email address because I don't know the exact address right now. And once I find it, I will communicate it to you through the lab students. So okay, so we have a question from Yulia. Can you present the computer vision? You can present this one. So you want to present this one instead of this one. It is possible, but your starting grade will be 8. If you want to start from 8, you can do that. So if you so I made the supposition that you would prefer to present the project with the higher grade. Okay, but if you want to present the other project for some reason, you can do it and you will start from the grade. So even the persons that are grayed out, they can choose to present the other project, but the starting grade will be lower. So if you accept that, yes, you can present whatever project you want. Okay, so I think this is what I wanted to say. Okay, and we will I will communicate the email address once I figure out what is the address, and then we will also communicate the presentation schedule and the links for the presentations. Okay, So I think that is it. Okay, so I see no further questions about this point, so I think we can close it here. We're already a bit past the time allocated, so thank you for participating, and yeah, see you next week during the presentation. Yeah, so you need to submit the code for everything that you tried and everything that so it's better to include everything in the presentation. So if you just include the code and explain only the main submission, you will probably get a penalty during the not a penalty. So there are some here 2 points that are awarded for the presentation and the documentation. Maybe it's not mentioned here, but it is mentioned in the slides. So we have 2 points that can so the mark can go down by 2 points if the documentation is not complete. So we will also consider if you present all the models that you submitted and also explain your strategy, why you tried the different models, how you obtain them, and so on. So yeah, if you decide only to present the best submission, then you'll probably not get the mark that the full mark that you expect. Yeah, I'm not sure about the question. What does it mean if it's like something like an optimizer? You mean the approach? It can be any approach that is a deep learning approach. So it can also be if your approach is based on some specific optimizer from the literature, you can just mention it. Or if you made these variations yourself, you can try to present them, of course. Okay, yeah, I assume so. If you just use the same code and modified some hyperparameters, of course you will send the last version. But I mean, if you use different models, like, I don't know, if you use the CNN and you also tried, I don't know, a fully connected network, you can present them both. Yeah, that's not necessary. So yeah, these are small code modifications, so I assume that a single code will be sufficient. Okay, so it really stayed too much, and I also have to go to the next lecture. So yeah, we will come back with some information regarding the presentation. So just keep in mind that next Thursday, starting at 10 a.m., we will have the presentations. Okay.